So in the previous lessons, we looked at the gradient of a scalar function, and we also looked at the divergence and curl of vector functions. What we're going to do here is extend that study to looking at the fundamental theorem of each of those. We'll first start off by looking at the fundamental theorem of calculus. Now, essentially, what this theorem tells us is that there are two ways to determine the total change of some function. One is we can consider the values at the endpoint, so at A and B. We plug them into our function, subtract them, and that will give us our answer. The other way we can do it is we can sum up the tiny increments as we go along. So we can sum up all of these, and we're going to get the same answer as if we subtracted the values from the endpoints. And that's given up here by derivative of some function with respect to x and integrated along that path from A to B. Now this is shown in one dimension. We're first going to look at the fundamental theorem for gradients. Now, what we can do here in order to determine the total change in T, such as the temperature in the room, and that's between 2 points, we can either sum up the tiny changes as we go along from A to B, or we can subtract the values at the endpoints. So here it's given by the gradient in the temperature and dotted with the infinitesimal displacement vector. And this is integrated over the path A to B, and this is equal to the values subtracted at the endpoints. Now we just have to recall what our infinitesimal displacement vector is. So dl is equal to dxx hat plus dyy hat plus dzz hat. So what we're going to do is just look at an example of this. So what we're going to do is consider a scalar t. I'm going to take the path from the point A, which is located at the origin, along to 1, 0, 0 to 1, 1, 0, and then we're going to finish off at point B, which is given by 1, 1, 1. Okay, so we're going to check the fundamental theorem of gradients using the scalar field t. So let's write up what our gradient is. So the gradient of t is going to be equal to the derivative of t with respect to x hat, plus the derivative of t with respect to y hat, plus derivative of t with respect to z hat. Okay, so what do we get for our scalar when we do this? So what we have is our gradient t will be equal to 2x plus 4y x hat plus 4x plus 2z cubed y hat plus 6 y z squared z hat. Okay, so that's our first step. Now what we must do is consider the path that we're taking. So the first path we're going to take is from the origin to the point 1, 0, 0. Okay, so what happens to x, y, and z along this path? Well, just look at y and z. So both y and z are equal to 0. These some changes we move along the path. So we have dy is equal to dz, which is equal to 0. X, on the other hand, x goes from 0
to 1. So here our infinitesimal displacement vector dl is equal to dx x hat. Okay, so now we must take the dot product of the gradient t with dl and what we get for this is 2x plus 4y dx. Okay, so remember x hat dot x hat is equal to 1, x hat dot y hat is equal to 0, and so forth. So now we know that y is equal to 0, so this now gives us 2x dx. So now we must take the integral of this between 0 and 1. So we get 2x dx. And this is going to result in, take 2x squared over 2, 2's cancel, this will result in 1. Okay, so this is our first side. So now what we must do is look at our second side. And for our second side, it goes from 1, 0, 0 to 1, 1, 0. So what happens here? We have x is equal to 1, z is equal to 0. X and z are not changing, so dx is equal to dz, which is equal to 0. Now for this side, y goes from 0 to 1, and our infinitesimal displacement vector is equal to d, y, y. So now I must take the dot product. And when we take the dot product, what results is 4x plus 2z cubed dy. And since x is equal to 1, z is equal to 0, we have 4 dy. So now taking our integral, between 0 and 1 for 4 dy, what we get is 4y, so we get, so that's for our second side. Now for the final side, where we go from, it's the third side, and now we go from 1, 1, 0, to 1, 1, 1. What can we say about x and y here? Here x is equal to y, which is equal to 1. X and y don't change, so we have dx is equal to dy is equal to 0. Z now goes from 0 to 1. And our infinitesimal displacement vector dl is equal to dz z hat. So what is our dot product between the 2 and dl going to give us? Well, now what we get is 6y z squared dz. Y is equal to 1, so we're left with 6 z squared z squared. And we take the integral of this, so we've got the integral of t dot dl from 0 to 1 of 6 z squared z dz. Now we take this integral, we're going to get 6z cubed over 3, so we're left with 2z cubed, so we're left with 2. Okay, so now what is our final answer? Well, what we must do is just sum these up. So we have the integral t dot dl is going to be equal to 2 plus 4 plus 1. Okay, so we get an answer of 7. Okay, now what we want to see if this is equal to the values, the difference of the values at the endpoints. Okay, so let's go back to our expression. Okay, so now what we want to look at is t of b minus t of a. Okay, and remember b is equal to 1, 1, 1, a is equal to 0, 0, 0, so between a we're going to get 0. So with b we're going to get 1 plus 4 plus 2, 1 plus 4 plus 2, which is equal to 7. And now we can see that the fundamental theorem for gradients holds.